propagation of computational tools for inference in society. Notwithstanding the great importance of the present views of explainable artificial intelligence, in the sciences and engineering, explainability very often assumes a different meaning. The premium is not so much on user convenience, but on the identification of the actual processes and phenomena in the natural world, what we call fidelity. So fidelity can be defined as the correspondence between the machine learning models and the actual reality that they are meant to describe. Just to have an idea, a flavor of the entity of the problem, for example, if you consider support vector machines, their models are always a sum of kernels centered on the support vectors, whatever the problem, in physics, medicine, computer science, economics, whatever. And so, of course, the structure of these models is not very informative and doesn't help a lot in understanding the dynamics of the phenomena behind. This is the outline of what I would like to say. I'll first try to describe, to introduce a genetic programming supported symbolic regression, which is one of the workhorses of the method that we have developed. And with this, we have improved the fitness function, both in terms of calculation of the errors and complexity quantification. I'll then describe the methods which exploit the synergy between dimensional and statistical analysis, before switching to the combination of physics-informed neural networks and symbolic regression, and all these things to improve fidelity. So let's start with a brief bird's eye view of genetic programming supported symbolic regression. The problem, I think, is obvious to everybody. You've got a database of validated entries, and you want to extract from this database a model. The traditional tools are fitting routines. You have to provide them with dependent and independent variables and a general mathematical model, general mathematical form for the model. And this, of course, must be derived from other sources, like, for example, previous theories of experience. And the maximum that you can expect from these fitting routines is that they manage to identify the most appropriate numerical values for the free parameters of the models. Symbolic regression is more powerful. You have to provide your algorithms only with dependent and independent variables. And it is the routine themselves we manage to identify which is the most appropriate form of the mathematical model to interpret your data. This is achieved with genetic programming, which, as you all know, is inspired by natural selection. So the methods work with population of individuals, populations of formulas in our case. The performance of each individual, in our case, the quality of each formula is evaluated with a metric, which is called the fitness function. And the individuals, the formulas, which have a better score according to the fitness function, are granted higher probability to generate individual of the following population. And the next generation is obtained by the parents via the application of the typical genetic operators, such as crossover, copying, mutation, so on and so forth. And this process is repeated until convergence. In our implementations, the formulas are represented as trees, which are very powerful. So typically, you don't limit to yourself in any particular way by adopting this form of knowledge representation. But the art of the matter is the fitness function, because the fitness function is the metric that you use to identify the better models, the best models that you want. And for the fitness function, we have adopted model selection criteria of the Ike and Big families. These are the criteria, the most used typical mathematical form. Please keep in mind that these are indicators that have to be minimized, so they are cost functions. The better the model, the lower the values of these indicators, and we can unpack them very easily. MSE is the mean square error of the residuals, so it is the mean square error of the differences between the data and the estimates of the model. K is the number of free parameters in your models, and N is the number of observations, so the number of entries in your database. You can see that you want small values for these indicators because you want the MSE to be small. You want indeed your models to fit well to data, to be close to the data. But in order to avoid overfitting, there is a penalty for complexity, K. If your models have an excessive higher number of parameters, they are penalized. So there is a form of parsimony already implicit in this criteria. So even if they are powerful and they have quite long pedigree, these fitness functions, these criteria are a bit crude, and both terms can be improved. Let's start with the first one, the MSE. Indeed, very often there is much more statistical information in the residuals that can be picked up simply by the MSE. For example, if you have a perfect model, the residuals should contain only noise. And at this point, of course, assuming, as it is typically the case, that the statistic of the noise is independent from the statistic of the signal, the mutual information between the residuals and the estimates of the models should be zero, because the residual should contain only noise. And of course, the better the model, the closer the model to reality, the smaller should be this mutual information between the estimates of the models and the residuals. And this mutual information, we included it in the original version of the criteria, multiplying the MSE by it, increasing significantly the discriminatory capability of the criteria. Also, the second term can be improved because it is well known that the number of free parameters is a very poor indicator of a model complexity. There are quite sophisticated theories and measures of complexity of functions, like the Wappling-Czerwonski or the Rademacher measures, but they are not fully adequate because first, they are not computable for large and important classes of functions, but also because they've been originally conceived to quantify the complexity of families of functions, not of individual models. And the two functions belonging to the same family can have a completely different propensity for overfitting depending on the numerical value of the free parameters. So we found much more useful to use as an indicator of complexity the number of changes of signs of the models in the interval covered by the independent variables. And so we have included here this number of inflection points into the criteria, again, improving the discriminatory capability. You can find all these, the demonstrations, and probably more than you want to know in this artificial intelligence review paper. Let's now switch to dimensional analysis. Dimensional analysis is a well-known approach to model building in science and in particular in engineering, because it can contribute to identifying more realistic and parsimonious models to describe particularly complex phenomena. The work on dimensional analysis was kicked off by Joseph Fourier in the 19th century when he observed that physical laws must be independent from the units which are used to measure the quantities involved. So any good physical law should be expressible in terms of dimensionless quantities. Unfortunately, even after a few centuries of work, dimensional analysis is not always exploited to the full, because what people do, they select the sets of dimensionless quantities a priori based on other considerations without any investigation of their statistical properties, and then they apply them directly to the data. We have developed a completely general and data-driven technique which integrates dimensional and statistical analysis in the same model building process, in the same learning process, with the help of genetic programming and neural computing. The methodology, by exploiting the potential of these machine learning techniques, allows extracting mathematical models in terms of dimensionless quantities directly from databases expressed in terms of only dimensional quantities, so without any prior guess about the form of the most appropriate dimensionless quantities. The method is a bit involved. First, you have to recognize that you can select and identify all the possible sets of reasonable dimensionless quantities with linear algebra. You can build these matrix here, where Q1, Qn are the dimensional variables, U1, Um are the units, and the entries of the matrix are the exponents of the various quantities that you need to obtain dimensionless quantities. The statistical properties and the proficiency of the various dimensionless quantities can be quantified with deep learning. So the overall method looks like this. You start with the database in terms of dimensional variables. You write the matrix, you equate it to 0 to identify all the possible sets of dimensionless quantities. With a deep neural network, you identify which are the most, which set of dimensionless quantities best fit your data. And then we have identified this set, you provide these variables to symbolic regression, which provide you a data-driven model, an analytical model of your problem. Again, you can find all the information that you want in this information sciences paper. But just to give you a flavor of the method, we have applied it to the classical problem of calculating the drag force around the cylinder immersed in a fluid. We simulated thousands of cases with hundreds of fluids. We provided as input to the routines just dimensional quantities like the inlet velocity, diameter of the pipe, temperature, so on and so forth. These are all the sets of reasonable dimensionless quantities, and in the end, the algorithms converge on this formula here, which links the drag coefficients to the Reynolds number, which from theory is well known for being the right solution to the problem. To conclude, I would like to describe this combination of physics-informed neural networks and symbolic regression, again, to improve fidelity. The motivation here starts from the consideration that traditionally, the procedures that we have to analyze experimental data, to formulate hypotheses, or to develop models suffer from a fundamental dichotomy. They are typically based either on numerical simulations or on purely data-driven methodologies. PINs, physics-informed neural networks, give the opportunity to overcome this dichotomy and to combine both previous knowledge in mathematical form, for example, conservation laws or symmetries, and experimental data in the same model building process. The prior knowledge, any type of prior knowledge you have about your physical model, is utilized in the training as a regularization agent that reduces the space of candidate solutions and steers the routines towards the most appropriate output. It's a very important form of data assimilation, which exploits the synergy between data and previous knowledge, allowing typically to converge on more realistic models and solutions. PINs were originally developed to identify partial differential equations. You can see the topology of one of these networks, the typical topology for this purpose. You've got your input here on the left, including time, then a deep neural network. Those outputs are differentiated and then given as input to the total loss, to the cost function. And you can see that in this cost function, there are elements which penalizes the distance to the data, so that favor models close to the data, but there is also a term here which favors models which are close to the governing forms of the partial differential equations that we have assumed should describe the problem. And with this network, of course, then the weights are identified, are selected with the typical backpropagation. The main motivation in our framework is the observation that very often the quality and quantity of the available data is not enough to apply symbolic regression directly. So the solution that we adopted is generative. We typically produce first a neural model with a PIN, and these neural models are called PDFNet, which implement some basic constraints, symmetries, conservation laws that must be respected by the physics of the problem. And with this PIN, with these constraints, we obtain a neural model that can be used to generate additional synthetic data. So the overall routine, the overall algorithm looks this way. You start with experimental data. With the PIN, you obtain a neural model, and then both the experimental and the synthetic data are given as input to symbolic regression, which identifies then the most appropriate analytic expression for your problem. This way, just to give you an example, I worked many years at the Joint European Torus, so a tokamak for research on thermonuclear fusion in England. And it proved very difficult in the past for decades to reconcile the measurements of the magnetic fields and the various diagnostics that we have to determine the plasma density. Contrary to this method, we had a very good reconstructed density with uncertainties. And you can see that all the measurements that we have of the density are very well fitted to what this new model obtained with this approach of combining pin and symbolic regression. All that and probably most that you want to know about this can be found in this paper in nuclear fusion. Just to conclude, in various scientific disciplines at the moment, there are ongoing activities to improve the model building process. Observational causality detections, physics-informed machine learning, and explainable artificial intelligence are just some of the examples. In this talk, we focus more on methods to improve fidelity, so to improve the coherence between the models and the real processes under investigation. This has been done mainly by deploying techniques which can take into account the prior knowledge about the problems at hand. These tools, just to conclude, I would like to emphasize that these tools can help in all phases of the scientific process, from the experimental design, the design experiments, to the interpretation, to the results, and the theory formulation. Thank you very much. I would like also to thank the scientific board for inviting us. And of course, if you have any question, I'll try my best to answer them. Thank you. See if I manage to. If you have any questions.